I have your midterm. Sealed in an envelope. So you will take it home, and when you're ready to work on it, you time yourself for 3 hours. When you're done, you close it back and return it to me. You are allowed to open your books and your scholar chapter 2, which is the chapter that I have in there. But no consultation, no other discussion, no other resources, okay? And I expect it no later than Wednesday's lecture. So you have plenty of time to dedicate the 3 hours.
You said Wednesday, right? You said Wednesday, right?
Yeah, Wednesday,
Just
right.
jump ahead.
Wednesday's lecture. So, the 4 people here, you don't open it until you are ready, and like I said, you time yourself for 3 hours. There are 4 problems in there. You should be able to do them in an hour, but you know, you have plenty of time to work on it comfortably. All right? So, I still have 2 people that are not in yet. They'll be on their way. If you have any clarification, you can email, all right? And what I usually do is I answer the whole class. I make your question anonymous. I don't disclose your identity, but I answer the whole class. Okay? So I'll be fair to everyone. And whatever information or corrections or help or hints, what have you, that I give will be to everyone. So don't hesitate to email me. All right? Don't come to me in the office hour because I won't be able to answer you alone, right? I need to answer the whole class. You can come to office hours for other things, not for the midterm. Any questions or clarifications on the procedure? Yeah, you need to have your tools next to you. You work on your own paper, you have to have your midterms and all these other things. Shall I repeat all the instructions again?
That's fine.
I'll repeat them at the end of the lecture, just make sure that those who come late will have the same instructions. All you need to know now is don't open the envelope now. Okay, so we've been discussing scattering parameters. And we gave a few examples, and I'd like to give some more, and also give some properties that sometimes are useful, so they can save us the trouble of working out the whole thing. And one of them, one of the obvious properties is if you have a symmetrical device, you don't need to work both the input and output, because output will be identical to the input, right? So if you have a device that is symmetrical like a piece of transmission line, say Z naught of the transmission line, and you're working with respect to some Z reference. We're going to use ZR for reference, like Poser is doing. Obviously, S11 is going to be identical to S22. And S21 is going to be identical to S12, right? Some logical things like that. Another useful property is if you have a lossless device. So this one here is symmetrical, right? If you have a lossless device, then the power doesn't dissipate. Power N must equal to the power out. What is the power N? Power N is in the A1 and the A2. Where is the power out? is in the B1 and the B2. So B1 magnitude squared plus B2 magnitude squared must equal to A1 magnitude squared plus A2 magnitude squared, right? So that means, if you really work this one out, you find that S11 magnitude squared plus S21 magnitude squared is the same as S12 magnitude squared plus S22 magnitude squared is equal to 1. In other words, if you take your matrix for the S parameters in general now, okay, and you sum the magnitude squared of any row or any column, you should get 1. So sigma Sij magnitude squared, all right? And we are working on the j, let's say. That's equal to 1, varying all the j's. Or if you do Sij sigma magnitude squared and working on the I, you also get 1. So if you either add one column vertically or one column horizontally, that will give you 1. There are properties like these that are useful and helpful in reducing the amount of effort that you need to do in deriving the S parameters. If you have we haven't had any of those, we'll see them later in microwave devices. If we have a unidirectional device, a device that sends power one way and in the back way it gives you 0, right? So it's obvious that the S21 will be something while the S12 will be 0, right? S21 will be the forward gain while the reverse gain would be 0, things like that. So what we are trying to say is, don't just get into the math and forget the physics. You look at your device, you try to use the properties of the device to reduce the amount of effort that you have to do, so you don't just write 10 equations in 10 unknowns and sit down and solve them, right? You can work out a smarter way to solving that. Okay, let's do some practical examples. Just take one or two examples. One famous example that is typical in transmission lines and waveguides and all that. Yeah, now, when Sean walked in, he reminded me that I made a mistake last time, okay, in the development of the reduction of the S parameters. And I can't remember if I remember exactly what I did. When I was doing the BS, that was gamma S, and I did the reduction of the S parameter of the cascade of networks, and I went that far and I got that as gamma N. Obviously, that's part of the source. What was meant by gamma N is here. Okay? So that was my mistake. I went too far. I got carried away and I kept reducing all the way to the inside of the source. That reduction is valid, but it would not be called gamma N, okay? Called something else. But gamma N stops here. This is the input of the rest of the devices. Correct? That's what I did. Yeah. One famous example that is used in when you have a junction of transmission lines. Suppose you have a situation where your transmission lines are going to branch, all right? If you want to call it a splitter, that's a good name for it. That's your main line is going to split into two different lines, right? So your main line is Z naught. Each of these lines is also Z naught, and you're going to connect these to each other. So if you simply connect them to each other like that, then you have two parallel impedances here, Z naught in parallel as another Z naught, and you connect that to your main line Z naught. So obviously your input impedance here is Z naught over 2, and you end up with a discontinuity. Right? If you have a splitter of that nature, okay, you are at home and your cable TV signal comes in and you want to split it in two rooms, right? You bring a cheap splitter that is basically connecting the center conductors to each other and outer conductor to each other, and guess what? You have a mismatch. You have standing wave. You ruin your signal. So what do? Well, we don't want to go fancy and design a matching network because that's something that is local and is just affecting us within some limited scope. It's not the end of the world. So what we do is we connect series impedances, all right? We'll call them Z X, ZX. From the symmetry, it turns out to be the same value anyway. You can call them ZX and ZY and ZZ, but you know, they're the same values. Because actually, what you'd like to do is also each one of those, you'd like them to see match. So you're going to see match this way, you want to see match this way, you want to see match that way. So what have we done here is we added a ZX here, and a ZX here, and a ZX there. Right? So what you have here now is Z naught plus ZX over 2, and you add ZX to that, that is supposed to equal to Z naught for matching. Right? In order to match, you need to add this whole combination and equate that to Z naught. And that will be the same from any other line that looks at this. Wherever you are going to be seeing the same thing. Obviously, if you solve that equation, that's an easy one. So 3ZX over 2 must equal to Z naught over 2. ZX is equal to Z naught over 3. So what you can do is, if that is a 75 ohm cable, that's a 75 ohm cable. I'm sorry, let's write that in a different color. So these should be 25 ohms each. You do that and you have a perfect match. But we are paying a price. And the price is power, right? Attenuation. We are losing part of the signal. All right? How do we see that? We can do the S parameters. That's typical analysis that we do. We do the S parameters. Now, to do the S parameters here for the sake of looking at power, I don't want to bother about this transmission line. Because that transmission line is lossless, this transmission line is lossless, this transmission line is lossless. So if I do the S parameters at these ports, I'll be getting the power relationship, all right, but I'm adding the characteristics of the lines, which is basically delay. Right? So I'll be seeing some more delay here, some more delay there, some more delay there, depending on the length of those lines. So I can just skip those for the sake of discussing power. So I'm just going to do a 3-port network, which is basically only the impedances. And this is supposed to be their second line. So that's the first network here, that's second network, and that's the third network. Now, if we had that much fun doing a 2-port network before using voltages and currents, you can imagine how much more you will have here. Right? So we're not going to use voltage and current. We're going to use the bounce diagram. Okay? And the way I'm going to do the bounce diagram is I'm going to do in succession here. So I do this first. I combine these to one impedance, and we decided that this impedance here now is, so I'm connecting here Z0 or Z reference. This is, I'm just going to choose the reference impedance to be the same Z0 here, which was the 75 ohm. So Z reference, I'm going to use 75. This is 25. This is 25. I'm going to work with numbers, okay? Shall we work with numbers or notation? Let's work with numbers. You can always redo it with notations. So I'm going to do this. I'm going to say that here's my S matrix. S11, S12, S13, S21, S31, S22, S33, S32, and S23, right? And that's my A1, A2, A3. And that's my B1, B2, B3. I'm going to zero these two. Here we are. We zero these two. Let me use a different color. 0, A2, and A3. That means terminate them into the reference impedance, which I chose to be the same as the characteristic impedance, for convenience sake. If you choose it otherwise, obviously the math is going to be a bit more complicated. So I kill A2 and A3. That means my B1, B2, and B3 over A1 will be these directly. So if I assume a signal here, A1, which is 1, that's my A1. Whatever I get back here is going to be S11. Whatever I get back, I didn't call gates here or ports. Let's call this 2. Let's call this 3. Right? Whatever I get out here is going to be S21, and this one here is S31. Now you notice I'm drawing S parameter arrows on the same circle, right? Which typically is voltages and currents. So that's really getting off the careful line a bit, right? But we are awake and we know what we're doing, okay? So this is not a current going to that wire, and that's not a voltage coming off that wire, okay? It's just we're drawing the arrows on the same diagram for convenience, and we are not going to mix apples and oranges. So this one here is 25, and this obviously is a 50, which is 75 plus 25 is 100, 75 plus 25 is 100, 100 paired with 100 gives you 50, 50 and 25 gives you the 75 that we are looking for here. So your A1 is 1, and you are getting a reflection of 0, right? We're not seeing any reflection. So right away, S11 is 0. And we expect that. That's what we meant by matching. Likewise, I can duplicate that here, because we said if you have a symmetrical situation, you don't have to do the thing more than once. So the diagonal of this matrix is 0. That means all 3 ports are matched. Okay? How much gets through? So we need to find out how much gets through here. Here we play the game of voltages, right? Because reflection coefficient is determined by the voltage wave. So if you have a plus minus voltage wave of 1, and again, doesn't have to be the same one as that, okay? It's a matter of ratio. You can pick any voltage, 10 volt, 5 volts, let's say 1 volt. That 1 volt here is going to appear here as a voltage divider, at 2/3 of a volt. Right? So a 1 volt here is going to appear as 2/3 of a volt right here. And it's going to be the same thing here, plus minus 2/3 of a volt. Plus minus 2/3 of a volt. That's actually how the bounce diagram in the frequency domain works out. That's how you do it. You use the voltage dividers, and that 2/3 of a volt is going to appear here, and it goes through the 25 ohm. Later there is a 75 ohm. So how much appears here? That's 2/3 times 75 over 100, which is a 3/4. 75 over 100. So the final voltage appearing here is going to be plus minus 1/2 of a volt. I'm writing everything in white. Voltages I'm writing them in white. 1/2 of a volt. Yellow was the yellow and red were the S parameters. So you put 1 volt here, and you see half a volt here, and you see half a volt there. Someone would say 1 volt split into 2 halves? No. It's just the way the mathematics worked out. So the S21 is basically the ratio between this voltage here and that voltage over there. So the S21 is 1/2. S31 likewise is going to be 1/2. Similarly, 1/2, 1/2, 1/2, 1/2. So let's sum the squares of any row of any column. Go back to this, I erased that already. So S11 magnitude squared plus S12 magnitude squared plus S13 magnitude squared is equal to 1 plus a quarter, I'm sorry, 0, plus a quarter, equal 1/2. So our signal coming in, power-wise now, gives a quarter power here and a quarter power there. The total power is 1/2, and the other half was lost in these resistors. 50% of your power is gone. Now, in some applications, that doesn't matter. Like I said, if you are at home and you're splitting your signal between two TVs, you have enough signal to give you the power that you want. That's an example of how S parameter shows you what's going on in a typical application. So when you buy that splitter, right, usually it looks like a small box and F connectors on the 3 ends, right? And usually that's sealed, right? If you manage to open that, you will find those 3 resistors in there. And sometimes they add a few more other things for improving the quality, compensate for some reactances. Can you imagine now if you're doing a splitter that splits the signal between 4 or 5 or 6 devices? It gets a bit more complicated. Any questions?
How do we know if something's symmetrical? Like, is it just, if it's passive, then it's always symmetrical?
Well, if you know it is symmetrical, obviously you have to know the physics of the thing or how it is configured.
Well, you said that knowing if it's symmetrical can cut down on working from the
Right,
S parameters, but
Right.
in order to find out that it's symmetrical, don't you need to find the S
Well,
parameters?
basically, if the circuit is given to you, it would be obvious that it is symmetrical. All right?
Okay.
If you build the device yourself, obviously you know that. But if you have a closed box and you don't know what's inside, you can't assume it's symmetrical. There, excuse me.
Sorry.
That's fine. There are tools in the circuit theory to figure out if it's symmetrical. You apply a certain voltage here, and you look at the current there, and all these kind of things. But in our applications, we're not going to resort to these kind of tools. If I give you a piece of transmission line, all right, and it's uniform, then it's obviously symmetrical. Right? That kind of thing. So it all depends on knowing what's inside. If you have an amplifier in your circuit, obviously that's not symmetrical. Amplifiers have all sorts of performance in the forward direction, opposite performance in the reverse direction. So that's not symmetrical. So either the circuit is given to us and we see it, or the device physics tells us that it's symmetrical. Otherwise, you can't assume it. Obviously, you have to go through the. So if I give you a T network, is that symmetrical or unsymmetrical? No. Unless I tell you the impedance, how much are they, right? So you can't assume, well, tell me what the impedances are. If this is X and this is X, the same thing, and that's a Y, okay, that's symmetrical. But if this X and this is Y, obviously it's not. Okay. Then you can't assume the symmetry. There are more rules for the S parameters, right? That I don't want to put too much time in. You can check them in the book. But I want to do another example. I'd rather do another example than lay down more rules. a device that is very common in high frequency applications or RF and microwaves is the directional coupler. The directional coupler is a device that basically senses the signal on your line, say that's your signal, and that's your reflection, and gets a sample of that separate, separates these two from each other. And we use that in the net analyzer. The net analyzer is sitting here having a monitor here, okay? Here's the net analyzer sitting, looking at your line, and the monitor is sitting there. And it's looking at the voltage here. That voltage is simply the mix of these two signals, right? It's simply the voltage across these two wires, or these two conductors. How do you separate them from each other? You need what we call directional couplers. We need to separate the A from the B. Otherwise, we can never get the B over A. How is that made? How is that manufactured? There are games that we play. Basically, let me draw the line as simply one line. Okay? What we do is, I'll make it a thick line. It's a different color, all right? So this one here represents the whole transmission line. Okay, the two wires. I get another transmission line, and then I provide some coupling. So that's some leakage coupling. That can be provided with like a very small capacitor or a very large inductor, you know, whatever it takes to just provide high impedance coupling, right? So only a very small signal that leaks out without affecting the main line. You don't want to do invasive coupling. You want to do, you know, something that does not affect, influence that. So this line here now, like, spies on this line without changing the characteristics of the main line. Let's say the distance between these two leakage things is D. Now let's do a signal flow graph here. You have a signal A flowing this way, a component of it will leak here, and what you get now is like a coefficient K times A. Okay? 1% of A leaked out. Assume that A is unaffected, so A continues to go. By the time it reaches here, it's going to be A e to the minus J beta D. Right? Now I have another leakage here. The other leakage was going to be also K times A e to the minus J beta D. That signal Ka is going to propagate both ways, this way and that way, and so does the signal here. The K is going to propagate this way and that way. So this Ka here, by the time it reaches here, is going to be, I need a space to write this out. I'm going to write it down here. It's going to be Ka e to the minus J beta D. It's the same, or a similar line with the same beta and same everything. And the signal here, when it propagates back, is going to reach here, and it's going to be A e to the minus J 2 beta D. E to the minus J beta D, another E to the minus J beta D. these two signals are mixing, and the total will be Ka plus, I forgot the K here, I'm sorry. So it becomes Ka times 1 plus e to the minus 2j beta d. I'm actually working with S parameters when I'm doing this. What I'm doing here, I'm following my signal flow graph, which is basically working with S parameters. The combination here becomes the sum of these two is 2Ka e to the minus j beta d. This one here, when you look at it, it's a sample of A. Obviously delayed by beta d, which is logical, right? That delay is no issue because that's really what's going to happen. Right? And the sample is 2K times A. So if K was 1%, you got a sample of 2% of your original signal. So I got a sample of A. I want to kill this one for a good reason. Because I want the B to come out this port. If I do the same exact thing with the B, likely here is going to be the 2KB e to the minus 2j beta d. So that's the sample of the B. Right? And if I kill this one here, I can also kill what comes here, because it's going to be again KB times 1 plus e to the minus j2 beta d. So if I put this